Hi, this is Reza Vazi, and in this video I will review the most important concepts in the object-oriented programming that are shared among almost all of the object-oriented programming languages. I will try to explain these concepts using everyday and relatable examples. In this video I will talk about classes and objects and their relationship and provide ample examples to make their relationship clear. I also will talk about the variables and functions within classes, and then we'll review inheritance, polymorphism, and encapsulation concepts. Classes are like concepts or ideas that exist in the realm of thought, while objects are real or materialized instances of those concepts and ideas. Classes can also be considered as blueprints or designs of real things, and objects are those real things like buildings or parts that are built off of those designs and blueprints. For example, Wright brothers, the inventor of airplanes, had an idea of a thing that could fly. That idea in itself could be considered a class, that blueprint or design. And the airplane that was built off of this blueprint by Wright brothers could be considered an object of the airplane class. When it comes to computer programming, you can consider classes and ideas those that exist in the source code of a program, and the program itself that is being executed in the memory as the object of those source code ideas. So the code will be the class, the actual thing that is running on the memory and is appearing on your screen are the objects of those classes. Computer programs are typically a collaboration between hundreds of thousands of such objects created off of the source code, the classes that exist on the source code. The classes and objects relationship also exists everywhere in nature, and that's how we could come up with it because we have learned from nature. Look at yourself, you are an object of class human. And if you have a pet dog or pet cat, they are also objects of class dog or cat. Human is a concept, but I, you, your friends and family, and the rest of the humans on the earth are objects of class human. We are the instantiation of class human. Classes consist of variables and functions. Variables typically create a reserved space for a varying attribute of a class that can be assigned to objects. That may sound complicated, but it is easy to understand if you pay close attention. For example, class automobile can have a color variable. That basically means each object of class automobile can have a color that is different from the other object, and the color of a car is considered an attribute of that car. The same thing goes for a pen. Pen is a concept that can have attributes of varying values such as its color, its ink color, or the writing head style and material. Each pen can have a specific color and a specific technology for its writing head. Now think about what are possible attributes of a human and accordingly what variables class human should have. Think about this for a few seconds. You may say skin color, eye color, height, and weight. Some of these attributes even change in an object's life cycle. Your height changes from when you are very young until you hit your early 20s, and then it starts changing again when you hit your 50s. At the same time, your height as an object of class human is different from other objects. So any attribute that can change either in an object's life cycle or from one object to another has a corresponding variable in the class that the object is created from. Classes also have functions or methods or operations. These words all refer to the same concept that are often used interchangeably in the object-oriented programming communities, and depending on which programming language you're using, one of them is preferred over others. For example, in Java, class functionalities are called methods, and in C they are called functions. Functions are part of a class code that define what objects will be able to do once they are instantiated or created. In other words, what functionalities or capabilities objects of a class will have upon their instantiations are defined in the code of methods of a class. Methods can also have their own attributes and hence their own variables. For example, imagine the brake function in an automobile class. The input to the function is the pressure by which the brake pedal is pressed, and this can vary from one instance to another. So the pressure here becomes a variable that its scope is limited to the brake function within an automobile class. So variables that you see in the body of a class can either belong to the whole class or their scope can be limited to a class function if they are defined within the code of a function instead of the main body of a class. To make the relationship between classes and objects more clear, let's consider a couple of more examples. Here we have class automobile, and you can see few of its general attributes showing up in the class diagram as variables. They are color, body style, and number of cylinders. To instantiate this class and turn it into an object, we need to give these variables a value. We give values of black, sedan, and 4 to color, body style, and cylinders respectively, and then we have an object. Just like that and just like magic, the class turns into an object. And you should not worry much about how this magic takes place because it is being taken care of through the runtime engines and compiler engines of the specific programming language that you will be using. However, if you decide to become a professional programmer, then you may decide to learn how this magic actually takes place so you can optimize it and make it better. Here is another example. We have class human with a few general variables such as skin color, sex, and sexual orientation. Once these variables take on a value, then we have an object of class human, as you see in this slide. Inheritance is another important concept in the object-oriented programming, which is very similar to the concept of genetic inheritance found in nature. It is the concept that enabled us to trace our roots back to single-cell organisms that appeared first on Earth hundreds of millions of years ago. We have closely observed the nature, learned how it organizes and develops itself, and took that idea to create our programming languages and programming logic. This programming logic makes programming practices much more efficient and maintainable. Basically, it enables us to start programming in general and add more features and specifications as we move forward and develop our own cyber organisms or software programs. Inheritance rely on the superclass and subclass concepts. A superclass can be considered as parent of subclasses, or in other words, subclasses can be considered as children of superclasses. With that analogy, you should expect that children or subclasses inherit all variables and functions of their superclass or parents. In addition to what subclasses inherit from superclasses, they can also have their own additional variables and functions specific to their design and need. Subclasses can also edit or override inherited superclass functions to their own specifications instead of creating new functions. I'll try to explain these concepts in the following example. As I mentioned before, we have created the object-oriented programming by looking into nature and learning how natural objects are related with each other and how similar or different they are. Let's start from the abstract superclass, life. The class life includes some variables and methods that define the basic form of life and what life is. We do not know exactly what life is, but we have some ideas. We do not call something that is static and doesn't change or move, like a stone, a live object. A rock is typically considered lifeless. So, for something to be alive or to be considered live, it needs to grow or transform, and that is the basic code. Now you can see that the subclasses of life, such as plants, fungi, and animal, they each have taken the base function or the grow and transformation and override it to meet their own specification for growth, change, and transformation. They also added their own specific attributes and functions in addition to what they have inherited from life. Now let's look into animals. Within animals, we have two other subclasses, vertebrates and invertebrates. They both inherit every variable and function that exists in animal. One function might be that animals can freely move within their environment as opposed to fungi and plants. However, this movement is quite different in vertebrates compared to invertebrates. Then within vertebrates, we have more subclasses such as fish, birds, and mammals. Again, all subclasses of vertebrates inherit all functions and variables specific to vertebrates, and the vertebrates version of all functions and variables of superclasses above vertebrates, namely animals and life. Within mammals, then we have humans, cats, dogs, and many more species or classes. All vertebrates, in fact, all animals and all life, have a reproduction function. It is one of those functions that comes with life and then gets edited and specialized as it goes through the chain of inheritance. Fish class reproduce one way, birds another way, and mammals also have a reproduction system that is shared among all of them in its general specification. The code for this system and functions gets further overridden and specialized as we go to each Mammalia subclass, and even each subclass may also have its very own capabilities and variables. For example, cats and dogs have a fair and fair pattern variable, while humans do not have that. Or humans have motor functions specifically designed to enable their hand skills, while these functions may not be present on other subclasses of Mammalia. Even though this example may not have been very accurate in terms of the bioscience behind it, but I'd like to think that it could give you the big picture here. The inheritance capability lets you program once and use it many times. For example, the code for life has been written once and then it is passed to subclasses, or code for growth and transformation is written once and then it is modified to meet the specification for each class. This is also how you write the code for a video game. Every element on a video game is fitted within this hierarchical inheritance structure. I use the video game example as many of you can relate to it, but this is the way that any good software application is designed and coded. In Java, the mother of all classes is called object. Yes, you heard it correctly, class object. This basically means that every class that you ever create using Java language will be a subclass of class object. Also, looking at this inheritance structure, you can see that We do not really have objects of classes such as life or class animal, but we have objects of class cat, sheep, and human. When superclasses do not have a direct object like in here, then they are called abstract superclasses. An abstract superclass is designed to provide code efficiency and enable a beautiful and working design. It is not a class that is directly engaged in the working of a program, but its existence is necessary for a good coding practice. An interesting concept called polymorphism. Polymorphism basically means many forms, or one command and many implementations, or many forms. It is mainly implemented through code override of superclasses within subclasses. For example, in a video game, an screen manager class sends the command shoot to different objects in the screen, and yet each object knows how to shoot. One shoots bullets and the other one shoots arrows. In a more basic form, the screen manager sends the populate the screen or appear command, and each object knows what its form will look like. A circle will appear as a circle, and a triangle will appear as a triangle. An enemy will appear as an enemy, and a friend as a friend. In the life kingdom, when an earthquake hits, cats knows how to run and a human knows how to run as well. The command here is to run, but the command will take many forms when it is implemented by different objects that exist within a given environment. The concept is related to polymorphism where one command takes many forms. Here, the idea is that each form does not need to know how other forms are being implemented or created. For example, when I command my pet to sit, I do not need to know how the dog carry out the command internally. In fact, a good design makes sure that internal processes of one object is not accessible or known to other objects that interact with it. When you push the brake pedal on your car, you do not necessarily know how the brake system works because its design and working is hidden from you. Encapsulation is a guiding principle for all object-oriented programmers and can be enabled through defining three levels of privacy of information or three levels of information hiding. When a function or variable is labeled as private, it means that its contents is only visible to itself and its input and output are only available to other variables and methods within its own class. As a loose example, you can imagine the stomach function in your body that is only known to itself, but its input and output are available to gastric class or overarching function within your body system. The next level is protected privacy. A protected method or variable is one that is working and its input and output is only accessible to a package of classes that together form a system or program. As another loose example, you can imagine when you have a pain in your body. The pain function makes itself known throughout your body and is only known to you, but no other object can know that you are experiencing pain if you keep it to yourself and do not express it. And public classes, variables, and functions are designated to those that are used as the object's interface with other objects. Their input and output and sometimes even their internal working is visible to other objects and can be accessed and modified through them. Here I used very general and inaccurate examples to describe principles of encapsulation. However, you will learn more accurate and context-specific usage of private, public, and the less common protected designations as you will learn more about your object-oriented language of choice such as Java, C, or Python. In this video, I've talked about the most important concepts that are shared among almost all object-oriented programming languages, and showed you how this kind of programming logic and design comes after our understanding of nature and natural phenomena. Object-oriented languages are very capable and can be used to model very complicated situations and complicated needs, while providing simple and manageable solutions for those complicated situations and needs. However, you should know that each object-oriented language has its own lingua franca and may use different words to refer to the same concepts that you learned on this video. The most important difference appears in the use of method and function. While they both refer to the same concept, Java language uses method and C family languages use function. Sometimes you can even see the word operations are used to refer to the same concept. The inheritance structure and capabilities may also differ from one language to another. For example, some languages let a subclass to inherit from more than one superclass, and others restrict a subclass to only one superclass. How the inheritance is implemented and coded can be very different from one language to another, but the concept itself exists in all object-oriented languages. The same goes for polymorphism and encapsulation. While they are shared among almost all languages, their working and implementation can be quite different from one language to another. So I strongly advise you to consult the language documentation in order to learn the language-specific lingua franca and language-specific structure for implementing inheritance, polymorphism, and enforcing encapsulation. Okay, I'm done now with the review of the important concepts in object-oriented programming languages. I hope that you enjoyed these presentations and you've learned something new from it.